Data transfer in CAD and CAM. Introduction. The CAD system is an interactive graphic system that enables data from the human interface to be transferred to machine interface through the CAD workstation. A typical interactive workstation could consist of the following hardware components: graphic terminal and operator input device. The graphic terminal is part of the interactive graphic workstation where graphics are generated, displayed, and modified, and the CRT. The operator input device permits the operator to create or modify an image on the CRT screen or to enter alphanumeric data into the system. Example: cursor control device, digitizers, alphanumeric and other keyboard terminals. Translators allow the supporting data of various applications to interface with the central product data management system. The application database management system associated with application workstation handle active data developed or required by the application itself. When a task is completed, appropriate data are transferred to the product developed by other application. When the data are transferred from active application status, they are processed and checked through an intermediate set of procedures and techniques to ensure that they conform to requirements, desired format, and completeness on the product component. CAD data structure. The computer-aided design database contains application model and designs and drawings and assemblies and alphanumeric information such as bill of material and text. The database also includes much of the interactive graphic software such as system command, functions, menus, plotter output routines. The database resides in the computer memory, that is primary storage and secondary storage. There can be exchange of data between the two memories when needed. A typical CAD data structure includes the following: basic graphic element, that is point and other elements; geometric, that is shape of the model components and their layout space; then topology or structure of the model, how the various components are connected to form models; and application specific data such as material properties, and application again specific analysis programs such as infinite element analysis. Transfer of data in various fields. Every CAD system has its own proprietary data format. Translation software are written to make it possible to transfer data from one CAD system to another. As the number of CAD systems is increased, the number of translators are also increased. Using a specialized translator is costly and difficult to message the number, such as n equals to c bracket n over 2 equals to n I raised power all over 2i bracket n minus 1 half. Using this, I see the equation. This is the equation. This is the equation. This is the equation. So the number of CAD system n and the number of translators capital N needed is as follows in table. This is the table. bracket, this is the table, n, small n, 2, 3, 4, 5, 6, 7, 8, and capital N, 1, 3, 6, 10, 15, 21, 28. Data transfer does not only take place between CAD systems, but also between CAD and CAM packages. A standard data transfer format, that is intermediate data format, helps to reduce multiple translators. If such a data file is employed, each CAD system needs only one preprocessor and one postprocessor, that is one set of translators. The preprocessors import data into the system while the postprocessors output the file into standard format. Data transfer file can be transferred as DYF, that is capital DYF, meaning data vertical field. File. Example, bracket 010, and DSF, capital DSF, that is bracket data horizontal field file. Example, 100, bracket 100. Various data exchange data has been developed in different countries and organizations, but the most widely used international standard are IGS and STEP. IGS means the international. It is formally called Initial Graphic Exchange Standard, but now International Graphics Exchange Standard (IGES). It was developed in the 1980s as the standard CAD data exchange format. It focuses on the encoding and storage of graphic information in a form that can be transferred from one computer installation to another for later reconstruction. It was designed primarily to serve the CAD and CAM community, so it contains several basic graphic primitives such as surface of revolution and spheres, as well as many different types of finite elements. Apart from graphic objects, it contains annotated drawing and the engineering information on mechanical parts and assemblies. IGES, which is International Graphics Exchange Standard, was developed for 2D and 3D and surface modeling data exchange. It is supported by almost all CAD systems. It has the general structure, frag session, start, and global, that is pre or post processor information, and directory entry, that is one for each entity, line type, color, and so on, and parameter and parameter data, parameters associated with each entity, and terminates. Geometric entities are encoded in the directory entity in the form of numbers. Example, 100, circular arc, 105, composite curve, 120 line. Each entry has associated parameters stored in the parameter data section. For example, for a line entity, we could have the following entries. Directory data, you have like 120, 20. Parameter data, you have like 120 is to 1.0, 1.0, 0.0, 3.0, 3.0, 0.0, etc. The above line, chord line. The above line, chord line 20 is defined from 1.0, 1.0, 0.0, bracket 2. 3.0, 3.0, and close bracket 0.0. So we have 3.5 step. I told you that the most widely used is international standard, which is IGS. Now we are going to be talking about step STEP. STEP, which is ISO 10303, 10303, close bracket 10303, close bracket, the international standard for exchange of product model data, which means the international standard for exchange of product model data, and was a major effort carried out by European countries under ISO, an effort that was parallel to STEP or to STEP, and was the product description exchange standard. It was the product description exchange standard, that is PDES, and later changed to for STEP projects in the United States. The goal of STEP is to define a standard file format that includes all necessary information to describe a product from design to production. That is the product life cycle. It also supports multiple application domains, that is mechanical engineering, electronics, etc., and contain product geometry, product functions, and a process plan for the product. The product geometry include drawing features, that's such as drawing features, CSG, and BREP, and it is also arranged into the application area, such as mechanical, electrical, AEC, etc. The standard is divided into categories. For example, the 01S series is concerned with definitional resource, and 02S with implementation method. The application protocols, APS, appears in the capital Z small ss series, and the 5 small ss series is known as application interpreted construct, AICs. It contains many standards like Part 001 overview, that is 1994. Part 042 geometric and topological representation, 1994. AP 201 explicit drafting, 1994. AP 203 configuration control design, 1994. AP 207 sheet metal die planning and design, 1999. AP 212 electrotechnical design and installation, etc. Of the preceding standard, AP 203, which is configuration control design, 1994, is the closest to IGS. It consists of a 600-page document covering more than geometry exchange. It includes assembly structure and configuration control information. Example: part versioning and release status and authorization data, etc. It covers a lot more than IGS. Development of device drivers. There are various device commands, as there are various types of device. For a line drawing device such as plotter, we might have set pixel, DD line, or such routine as DRWABS and P bracket point inside. In all cases, device coordinate must be sent to the device in question, and each device has its own built-in coordinate system. Application can be written for device without regard to the specific device doing the drawing. The type of coordinate system suitable for this device independent application is normalized device coordinate, graphic kernel system, that is GKS, defined NDC as sequence region with the lower left corner, that is bracket 0, 0, and upper right corner, bracket 1, 1, as shown in figure 3.1 below. For example, to draw a line, we use the following procedure line: NDC, bracket S1, Y1, S2, Y2, real, and draw a line from S1, S2, S2, Y2 in NDC, and use a different version for each device. For each device, version look like these two applications. The line is displayed approximately at the center. A handy example of the use of line NDC as a bracket is boss, which draw a rectangular having opposite corners. Example: S1, Y1, and S2, Y2. The boss has horizontal or vertical side. Boss simply join together the corners of the boss with 4 cells of the line NDC. Example, figure 3.1b. Procedure: boss S1, Y1, S2, Y2, real. Draw the boss with one corner at S1, Y1 and opposite corner at S2, Y2. This is the boss. This is the boss. Using normalized device coordinates S2, Y2, S1, Y1 display. Building a curve out of control point. A curve PT can be described by a set of points. Bezier curve were developed by P. De Castillo in 1895, and independently by P. Bezier around 1962. They were formulated as ingredients in CAD system at 2 automobile companies, Citroën and Renault, to design shape for car bodies. The Castillo algorithm. The Castillo algorithm uses a sequence of points to construct for each value of t of interest a well-defined value for the p bracket t. Thus, it provides a way to generate a curve from a set of points. Changing the points change the curve. The construction is based on familiar in-between or linear interpolation steps that are easier to implement. A parabola based on 3 points. Considering 3 points PO, P1, and P2A as shown in figure 3.2, choose some values of t between 0 and 1 and locate P0, that is the fraction t of the way along the line from P0 to P1 similarly, and locate P1 fraction between the endpoint P1 and P2 using the same T. This is standard in between, and we know that the new point can be expressed as follows. P0 T equals to 1 minus T P0 plus TP, equation 1. P1 T equals to 1 minus T close bracket P0 plus TP2, equation 2. Now repeat the linear interpolation step on this point again using the same T. Find the point P2, P square 0 T that lies the same fraction of the way between them. This is the Castillo algorithm. This is what we mean by Castillo algorithm. This is it. If the process is carried out for each between 0 and 1, the cone PT equals to P square 0 T will be generated as shown in figure 3.3. It should note that for T equals to 0.1, for T equals to 0.5, it must simply by finding the midpoint between midpoints for the three given points. By direct substitution, equation 3.1, 3.2, 3.3, Pt equals to 1 minus T close bracket square P0 plus 2T bracket 1 minus T P1 plus T square P2, equation 3. Since this is the quadratic in T, the curve is a parabola. It will still be parabola even if it is allowed to vary from S to S. It may seem a bit strange, but the method generalized immediately repeated linear interpolation for L plus 1 point. The Castillo algorithm for L plus 1 point. For a given value of T, we successfully build up the R minus T generation of in between P, then T from the previous R minus 1 T minus first generation, PR over T equals to 1 minus T close to bracket 1 minus T close bracket P raised by our R minus 1, comma T plus RPI plus 1R minus 1T. For each generation, R equals to 1 is to L, and for 1 equals to 0 and L minus R. The process starts by using P for PO. The final generation PNOT is called the Bezier curve for the point P. PL, the points themselves are called control points or Bezier points, and the polygon formed by this point is called control polygon or Bezier polygon.